One of the most interesting and useful things that an LCR circuit can do is it has a resonant frequency. So I want you to consider this setup here. It's just a nice simple LCR circuit, but this one has a frequency variable power supply. So it introduces a source voltage into the circuit, but we can change the frequency with which it changes. And what we find is that we get a certain current out of the circuit. The really interesting thing is that depending on how we change the frequency, we'll find there's a place where we suddenly get a huge, well not suddenly, but we get a huge current, a maximum current. So I hope you can see here that in the beginning, you know, and at the ends, the rest of the circuit, there's a big impedance in the circuit. Okay, we know because the reactance of the capacitor is 1 over omega C. That means that if omega, the frequency in the circuit, if the frequency is really, really big, then this is going to be really, really, really small. On the other hand, I hope you can see here that if the frequency is really, really, really big, then this is going to be really, really, really big too. So at the beginning, at fairly low frequencies, and at the end at fairly high frequencies, you're going to get times where either the reactance of the capacitor or the reactance of the inductor are really big, leading to the impedance of the circuit being really big. But there will be a frequency for which these two things balance out, and there's a minimum impedance in the circuit. And that minimum impedance, naturally, being the smallest possible impedance the circuit can have, gives us a really, really, really big current. So I hope you've guessed what I'm getting at here is you get resonance at the point where these two things cancel out. And it's hard to see how that happens, but it does. What happens is, and I hope you can imagine this, so let's just pick any old frequency. At any old whatever frequency, we might get this much inductance, reactance of the inductor in the circuit. We get a certain value for R, which doesn't change with the frequency, and we get a different value for the reactance of the capacitor. And when we find the impedance of the circuit, so this here comes off that, okay, and what we get is a relatively big impedance. I hope you can see that if we could find a time, if we could find a frequency for which these two things were the same, they would cancel each other out. What we'd find at that point was that our impedance was equal to the resistance in our circuit. And I hope you can see that if there's ever any kind of reactance in the circuit, this here, this impedance is going to be bigger than R. Okay, and I hope you know you can see that from using triangles. It doesn't matter whether the reactance of the capacitor is big and the reactance of the inductor is small. It doesn't matter. As long as there is some reactance in the circuit, some overall net reactance in the circuit, then the impedance will be bigger than R. To get a resonant circuit, we want the impedance to be equal to R. Therefore, we want to find the frequency for which the reactance of the inductor and the capacitor balance out. That would be a resonant circuit. And fortunately for us, we can do some nice, beautiful, simple mathematics to do with it. And what we find is that if the reactances are equal, you'll get maximum current. That means the voltages across it will be at their maximum. And what we find out is that we can just continue using Ohm's law. And this here is, this resonance is at the heart of how radios work. So a radio receiver, as I'm sure you know, you can turn the dial and you will skim through certain radio frequencies. This is literally what you're doing. You're literally manipulating an LCR circuit on the inside of the radio to find a resonant frequency that matches up with the frequency of a radio station. And that's really useful to be able to do. If you want to find out if it's safe to go home after a tsunami, you know, you can't use your cell phone because that's dead. There's no TVs because the electricity's out. But radios are incredibly useful in situations like that, even though they're maybe not as popular as they used to be. So in class, we're going to be solving quite a few problems using this application of LCR circuits.